everyone. It's my great pleasure to welcome you all to our second talk in our series on the cognitive science of generative AI, and to introduce today's speaker, Cameron Buckner. Cameron, unlike many of us, has been sort of at the coalface of trying to draw out the philosophical implications of AI, and in particular deep learning models, for almost a decade. She's currently a professor at the University of Florida, where he holds the Donald Cronin Chair, Endowed Chair of the Humanities, having moved there quite recently, if I understood this correctly, from the University of Houston, after a stint in Germany as a Humboldt Fellow, which followed on from a PhD in philosophy at the University of Indiana, Indiana University, Bloomington, and dual undergraduate degrees from Texas Tech, one in computer science and one in philosophy. As I've already said, he's been working on these topics for a long time. Much of that research is summarized in his recent book, that appeared last year with OUP, From Deep Learning to Rational Machines, which I'm going to plug shamelessly here, so he doesn't have to. I hardly recommend it. I'm about halfway through. And I'm really looking forward to him telling us what he makes of large language models as models of human reasoning. So over to you, Cameron.
Okay, thanks for coming, everyone, and thank you for the invitation. I'll jump right into it because I'm definitely not going to be able to get through all the material. I've got sort of an hour-long talk, and I'm going to cut like the last 25%. It's more philosophical, and we can come back. I'll leave it as a stub. We can come back to it if you want. But as Ulrika mentioned, I'm evaluating these recent claims, especially. We'll get to O1 kind of at the climax of the talk. Very ambitious claims about the ability of recent large language model advances to model human reasoning or reason themselves. So a broad overview of the setup of the talk. I'm using a kind of tree metaphor here. And what I'm going to do is kind of set up different ways of evaluating this claim that large language models might be good models of human reasoning. The first twig on the first branch is we could look at good or correct performance on reasoning tests. You've certainly all seen a lot of these claims in this neighborhood. The second twig, and we're getting sort of like, I think, better quality evidence as we go down the first branch, is looking for distinctive mistakes on reasoning tests, in particular human-like mistakes. On the third twig would be scrutinizing inner chain of thoughts. This is particularly in O1, which now has kind of a private internal chain of thought it does before it gives an answer on a question. And then the fourth twig, I probably won't be able to go through it all, but I'll at least plug a paper that Raphael Milliere and I have that reviews a bunch of mechanistic interpretability methods that I think is actually the best form of evidence. And this is the part that I almost certainly won't get to, but I can tell you what I mean at the end. Even if we don't think these models are good models of the internal mechanisms of human reasoning, they could still be models of reasoning as it's present in human textual culture, and that's not nothing, especially from a philosophical perspective, but I'll probably won't get to that. So Ulrika already mentioned my book, so I'll kind of move very quickly here. If you're wondering what is deep learning, a lot of people will tell you it's just B.F. Skinner reincarnated. If you want 450 pages of saying no, that's not the right interpretation, that's kind of a straw man, looking at lots of details of recent models and position papers by key figures in the field. Please check the book. The main question of the book is what kind of empiricism should be attributed to deep learning? And if you ask the rationalists or the nativist critics of deep learning, you get a very impoverished view of what empiricism is. Gary Marcus in particular has kind of put this in pseudo-formal garb. He says you could think of cognition as a function over four variables, where A is innate algorithms, R is innate representational formats, K is innate knowledge, and E is experience. And he says a true blank slate, which is the view he attributes to the empiricists, would set K and R to 0, A to some extremely minimal value, like a single learning rule for adjusting reinforcement weights, adjusting weights relative to reinforcement signals. And then he tacks this view on Locke. And if you read even the next few pages of Locke or really any other major empiricist, you'll see they appeal to a whole bunch of stuff that doesn't fit this really impoverished view of what their palette would let them paint with. So this is a straw man view. Very quick gloss on what's missing is that I think all of these critics read both the classical philosophical empiricists like Locke and Hume and James and current deep learning theorists as not getting cognitive architecture, as having to think that you've got to sort of learn cognitive architecture, or what philosophers would have called a faculty architecture, from that one or two simple learning rules. And this is just obviously inconsistent with the vast majority of what most of those theorists say. So you shouldn't let people say that and get away with it. So this is, for example, a kind of typical empiricist faculty architecture from Peter Millikan, who's a Hume scholar. And you see familiar things. Of course, you get the perceptual faculties, but then things like imagination and this reflection, in particular, memory. Reflection is the one I'm mostly going to talk about today, and it's one that didn't make it into the book. So what I do in the book is each chapter is centered on a particular faculty that would have been part of the cognitive architecture and the empiricist toolkit. And I talk about how some of the major insights have already been integrated into deep learning models of various architectures that already exist. But I mentioned I didn't quite get to reflection, which was the big one for all of the empiricists, and I'm going to talk a little bit more today. I think I didn't get into it in the book because the technology wasn't yet there, but there have been big strides in the last couple of years in that direction that we'll be evaluating today. Reflection being the most important faculty for human reasoning, I think. I call this general approach, and I say this is the kind of empiricism that should be attributed to the whole strategy, both historical empiricists and recent deep learning modelers, is the new empiricist dogma, and that's just an acronym standing for Domain General Modular Architecture, where the idea is you've got a bunch of different modules with different basic computational principles interacting with one another to kind of bootstrap cognition to greater degrees of flexibility and generalizability. Okay, but I'm going to focus in particular just on LLMs today and recent claims that LLMs are good models of human reasoning. So what are they? They're large language models. As you have undoubtedly heard, they have billions or trillions of parameters, takes a lot of energy to train them. They're trained on some non-trivial portion of the entire internet. And then later, now there's all kinds of other post-processing steps they go through. They're fine-tuned on instruction sets to be better at solving certain kinds of problems. They get trained on code from GitHub, which interestingly improves their reasoning performance, and also reinforcement learning from human feedback. And now in models like O1, they also have a kind of additional rounds of reinforcement learning on self-prompting that we'll talk about in more detail later on in the talk. But these are just things like the GPT series, Claude, Llama, Gemini, and so on. Now, I want to stress in the very beginning, I'm not going to have a chance to go through how transformers really work, but I do want to try and dispel a few misconceptions, especially if you're swayed by a kind of stochastic parrots line from Bender and Kohler that it's just, nothing that could even be eligible for being evaluated as cognition. I'll try to disabuse some of those notions early on. There's in particular a very long tradition going back all the way to the 60s of the idea that the kind of vector space semantics you find in these models could be vectors could be bearers of meaning in a significant sense, and the recent advances in deep learning are part of this tradition. But they also enrich this tradition in things that weren't possible until just a few years ago. The basic idea of a vector space semantics, just to give you a really quick idea, is that you represent the meanings of words as locations in a kind of multi-dimensional vector space, right? And you can handle quite a lot of semantic phenomenon in this way. For example, you have this word bank that could be ambiguous. It could mean like riverbank, or it could mean financial institution. And you might use context in which the word occurs to try to disambiguate this word, right? So you could say, well, if I had a model that could, put bank sort of kind of ambiguously in between a cluster of words like building, money, and credit that has to do with financial transactions, and another cluster that has to do with river, water, and ground has to do with riverbanks. If I could look back in the context of the word and kind of push this vector around to be closer to one cluster and further from another, then I could kind of disambiguate the meaning, right? So cosine distance here is a kind of proxy for semantic similarity or relevance in these vector space models, and the ability to move vectors around can allow you to kind of dynamically accommodate changes in meaning as a result of, for example, context. And all of the advances in transformers are based on this kind of basic idea of moving vectors around in vector space to capture aspects of their semantics. But I do want to stress that, the technology, especially in the last 3 or 4 years, has come a very long way to something that might be different in kind. This isn't your advisor's 1980s connectionism. So in particular, the key mechanism of transformer that differs from the earlier vector space models is they use this self-attention mechanism. Long story short, it breaks the representation of each word's meaning into actually a set of three vectors called the query key and value vectors. It doesn't really matter for present purposes where that language comes from or what exactly they do. The important point is it allows you to much more dynamically adjust the meaning of a word in a particular context, which allows you to capture a lot of other semantic and syntactic phenomena that you might not have been able to otherwise. So I'll jump ahead for time. So moving vectors, the idea is that the key represents the intrinsic meaning of a token across all contexts, and the query represents the meaning of the word's context in the current prompt. And the value represents the meaning of the word as modified by the context in which it occurs. Then there's many self-attention heads that are kind of stacked in parallel, and then many layers of self-attention heads that are taking input from previous layers. So different self-attention heads can specialize in different aspects of a word's contextually modified meaning in a particular prompt. For example, you could have one that's maybe focusing on pluralization, another focusing on subject-verb agreement, another focusing on the way an adjective modifies the verb, another, all kinds of different aspects of the word's contextually modified meaning could have different self-attention heads specializing in them. So by dynamically moving the word's meaning around in these ways, you can accommodate a wide variety of phenomena like ambiguity, anaphor, grammatical relationships, and even learn entirely new patterns on the fly. That is, patterns that weren't present anywhere in the pre-training set, but are given only for the first time in a prompt. So this is one of the things that first people got people really excited about the potential for reasoning in these models, is it looked like they could now do few-shot learning of entirely new patterns just given to them in a prompt. So not 1980s connectionism. It actually looks a lot more like this. I'm not going to explain all this. I think I have a anaphor example. Yeah, so if you're asking what is the model's representation of a single word's meaning, it's like this whole thing, right? You can visualize the attention heads and how all of the different aspects of the context are modifying a word's meaning and context, but it's very daunting to try to interpret any particular functional role of any one of these heads. It's going to take a lot of difficult interpretability work. But if you focus on particular examples, you can get an idea how this could handle something that looks like it would involve things like role variable binding operations, like anaphor resolution. So if you take, one of Asimov's laws of robotics, a robot must obey the orders given it. It was going to have kind of intrinsically a very underdetermined meaning, right? It's an anaphor that you might need to resolve to any kind of previous target. And in this case, it should resolve it to a robot, right? And so what the attention head does is it uses the query term to see that a robot should be very heavily weighting the meaning of the word it in this context. And so then later on, any operations that are consuming the value modified by that query term for the anaphor it is going to, in some sense, know that it's pointing back to the robot. Goyal and Bengio have a kind of position paper where they argue that this kind of mechanism turns transformers into things that are just processing vectors to machines that are processing sets of key value terms, and they argue this gives you a kind of variable binding because you can now dynamically bind the particular vector representation to all kinds of different topics. There's a bunch of other great stuff from, say, Anthropic AI's blog posts to argue that there's very content general operations going on in these systems. In particular, they argue there's this mathematical abstraction called the residual stream that can work kind of like a read-write memory, because the idea is the vector space for these models is, 20,000, 40,000 dimensions. It's a very big space in higher dimensional vector space. And you can get a kind of coordination between attention heads, where one attention head can learn to write information to part of this, what they call residual stream, which is just kind of a reserved area of the higher dimensional vector space, that another attention head later on can learn to attend to particular bits of information that are written in this space. And it gives them a kind of read-write memory access where they can pass information to one another through the rest of the operations in kind of a fully content general way. It's not bound to particular patterns in the training set. So this is just an example. You can see there's this composition relationship that gets built between different attention heads at different layers. And this gives you in particular, they argue this allows you to explain some of the in-context meaning of entirely new patterns that you get in these models. In particular, you get this phenomenon called induction heads, where two heads learn to coordinate this entirely content general operation, that one will pick up a new pattern in the context at an earlier layer and then pass it along to the other one at the later layer so they can then continue the pattern. You can get kind of mundane, just pattern copying novel in context, like, you see Ralph, it picks up the token R and it figures it needs to complete the pattern Ralph. But you can also get some more flexible behavior where it's not just doing Ralph and outputting Ralph from earlier in the prompt, but learning because the context, for example, suggests it needs to be a capital R. It should actually capitalize the rest of the word, even if it's never seen the word Ralph capitalized. These are just very simple toy examples from two-layer attention models. And the thought is if you scale this up, they can do a lot more flexible generalization behavior from just a couple examples in a prompt. And that in part explains some of the reasoning-like behavior we see in these models. Bunch of other pre-training stuff I already mentioned. Post-training stuff happens in these models. Should complicate any very simple picture that anybody tries to tell you. They're just regurgitating patterns from their training set. Okay, so now let's talk about, we've got these models. They're learning novel patterns in the prompts, even from just a few examples, and doing this really flexible, sometimes very surprising behavior. Does this mean that they're good models of reasoning, as some of the industry boosters have claimed? Well, let's think of different ways of scientifically evaluating that question, given that we are interested in psychology and neuroscience and so on, and good philosophy of science measures of responsible evidence evaluation. Well, the first line of evidence that you have almost all surely seen are just performance success on, say, standardized tests. So you've probably all seen in the news and in research talks these results that say GPT-4, for example, can perform much better on an array of standardized tests, AP tests, GRE, SAT, IQ tests, than most humans, certainly better than a lot of other previous models. And you continue to get these big performance boosts even over previous models on some of the more difficult tests that you might think require reasoning. Is that, should that be convincing to us or not? You might worry. I mean, of course, to start with, the obvious worry is that they've probably seen a lot of SAT and AP tests and so on in their training sets. And so they might be matching kind of approximately previous versions of these questions in their training sets. You might also worry about the artificiality of these tests. One way of trying to get around just showing performance on previous standardized tests is to look at a whole big range of different things. And the Big Bench project would be the thing to look at if you had this kind of inclination. I sometimes call this the paper with a bazillion authors. They're approaching CERN levels of authorship on these papers, but it's because everybody who contributed a task to this test was a co-author on this paper. This is, I think, out of date. I think they might have 250 or 300 tasks now, but they at least had 204 at the time that I did this screen grab. And it was meant to be like, whatever capability you're interested in, let's just build a kind of training set and then a hidden test set that we can assess how good these models are at solving this type of problem. And in particular, you can find that indeed there is steady progression towards better results as the models get bigger and more architecturally sophisticated. In particular, chain of thought prompting led to a bunch of big gains. I'll talk more about chain of thought prompting later if you haven't heard that term before. I got some big gains on a lot of different Big Bench tasks, including reasoning tasks. And there's a whole section of there on reasoning that you could go look at and see how whatever model you're interested in is performing on that particular subtype of reasoning task. But one general worry that I have with this entire twig of the branch one based on success on performance tests is that we really don't know for any particular result whether it's just kind of copying a pattern from its training set. There's one way of illustrating this possibility that's a thought experiment that I do think is worth returning to from Ned Block, where he said, well, imagine you have a very large research grant and you could employ experts from all over the world to imagine any potential question that you could ask an artificial agent, and they just kind of precompile a really good response to that question uh, in some very large database. If you weren't restricted on the resources of that database, you could sort of package in an answer to any question you wanted there, and such a system would pass the Turing test, but intuitively, it's not intelligent. I sometimes get people who will bite the bullet here and say, even granting all of the structure of the experiment, if it could really give you a good answer to any question you would ask, why not say it's intelligent? I say, well, how far are you willing to bite that bullet? Imagine you have a student in your class who just managed to hack your computer and steal all the answer keys to all of your quizzes, and they get 100 on every question by just rotely memorizing the right answers without knowing really understanding any of the course materials. Are you really going to tell me that that student is just as intelligent as another student that kind of internalized all the material? I don't know what to say past that point, except they're not as intelligent, right? And there's given the amount of the internet that these systems have seen, it's kind of a real possibility that, I think one thing you find is if you're trying to really come up with a question that nobody has ever seen before on the internet, you find humans really aren't as original as we think we are sometimes. And there's really not that many different ways of putting together conceptually interesting questions. You'll often find so-called data contamination, that it really is present in the training set. And then it's a huge epistemological problem that these training sets are immensely valuable proprietary databases for these systems, and for the companies, and they often don't want to let you have access where you could verify data contamination for yourself. So I think the right way to regard this, a lot of people regard this kind of worry saying, oh, well, all they do is regurgitation, right? This is the stochastic parrots type line. But I don't think that's the right way to interpret it. I think the right way to interpret it is it's always kind of a null hypothesis that you want to be able to overcome, that whatever result you get from them in any particular case could be a regurgitation effect. And what you want to do is be able to provide evidence that it's not in this particular case. In particular, I think that this thought experiment, doing away with the sort of fanciful metaphysical philosophy assumptions here, it remains an empirically relevant possibility due to some technical results from Zhang et al., which they did an experiment where this was on a DCNN, but they had many millions of high dimensional inputs and they just randomly scrambled the labels, right? And they found you could get almost zero training error on these models, where from a God's eye perspective, there are no abstract principles governing the linkage between the high dimensional patterns in the inputs and the right answers. It could just rotely memorize the right label, randomly assigned to every single input in this very large high dimensional training set. Of course, it then gets zero test generalization performance. But the point is, it has this enormous memory capacity, certainly much larger memory capacity than humans do. And so, we know from this and all kinds of other direct evidence that any particular, even quite sophisticated looking result we get from these systems could be a memorization effect. So how are we going to try to control that? Well, some people inspired by a kind of psychometrics tradition understand the danger of memorization, and they want to try to design tests that should overcome the threat of memorization in any particular case. Francois Chalet at Google, I think he might be leaving Google now, but I think he has one of the most sophisticated approaches to this, and he's designed what he calls the abstraction reasoning corpus. He wants to focus on intelligence not just as kind of G factor, but in particular what he calls skill acquisition efficiency. And he wants to build a set of tasks that are he can sort of guarantee are not in the training sets because they're very highly artificial, but they are going to measure the system's ability to acquire solutions to new tasks in a very quick and efficient way. He, for whatever it's worth, is kind of beholden to nativism, in particular, a kind of core knowledge approach to innate knowledge. And he understands that you can't have an entirely prior-free approach to skill acquisition efficiency. So what he wants to do is design a bunch of tasks that are going to assess facility with human priors, in particular things like, do you have a concept of object? Do you have a concept of number? Do you have a concept of causation? Do you have a concept of agency? And use those to get very efficient acquisition of new solutions to very abstract tasks. These are some examples of what tasks in the abstraction and reasoning corpus look like. For a human, I think it would be pretty hard to even figure out what the task is you're being asked to solve here. You can maybe see it a little bit better. This one is meant to check various aspects of object priors and pathfinding. So the idea is you're given some samples of completing a green line that looks kind of like a pathfinding problem, and then it's given a new version of that in the test part of the assessment. This is just to say there are people that are taking this type of blockhead type objection seriously and are trying to find tasks that could solve it, although the tasks end up looking, pretty artificial and ecologically invalid at the end of the day, if you try to step back and ask where we started and why we were interested in this in the first place. I also want to point to this book by Jose Hernandez Arroyo for anybody who's interested in this kind of psychometrics inspired approach. This is a very thorough book, and there's a whole separate tradition of this approach in AI that focuses on algorithmic information theory, and there's not time to get into the details there, but just look at Chalet and Hernandez Arroyo's book if you want to get deeper into this line. I do think, however, that no refinement of tests is really going to answer the fundamental problems we have with this approach, which is despite the name abstraction and reasoning corpus and the psychometrics inspired tradition generally, all these performance metrics may be ill-suited to assess reasoning, at least in the sense in which philosophers and I think many psychologists are interested. It's just designed to assess general intelligence if you believe such a thing exists. Again, there's no real, the psychometrics tradition doesn't give us any really conceptually motivated idea about what intelligence really is. It's just a set of correlations on various performance tests that are real in humans, but there's no reason to think that those correlations are going to be tracking the same underlying things or have the same kind of validity in a system that's very unlike us under the hood. And it remains purely performance-based metrics, so it can't assess any of the kind of internal algorithmic transition type stuff we might be interested in reasoning, like sensitivity to evidence or transmission of internal confidence or truth preservation or sensitivity to justification. These purely performance-based tests really aren't the right type of thing to give us any of that. So another slightly better form of evidence would be the ability of these systems to reproduce biases and errors in human performance. So here we're not looking, do they get the right answers to questions that we ask them, but do they kind of spontaneously, without being trained to do so, reproduce human mistakes? So this has long been an idea in the connectionist modeling tradition that if you spontaneously reproduce human errors, it's maybe more likely to be a good model of your reasoning than if you only reproduce success. For example, McClellan and Rummelhart in their famous discussion of a model of verb conjugation, note that it made some overgeneralization errors that classical models of verb conjugation learning didn't, like going through this intermediate conjugation from break to broked in the past tense to finally learning the correct irregular broke. And the thought was that suggests that, like little kids, they're kind of overgeneralized this conjugation rule before learning the irregular correct solution. So we might ask, do large language models recapitulate human errors spontaneously in this way? There's in the past been intense interest on whether deep convolutional neural networks, these are for computer vision, recapitulate, say, human shape bias, which is a bias we know that humans, that is, they tend to categorize by shape rather than by other features like texture or color. So, for example, one study finds that if you mark up a picture of a cat in kind of elephant skin texture, the models will think it's an Indian elephant, whereas most human raters will say, no, I think it's a cat. And that shows kind of a divergence in I think these type of stimuli are a really interesting thing. What's the right answer? Because, this is a very artificial stimulus and it's not clear that there is a right answer, but I'll set that aside maybe for the Q&A to return to. But we can still ask these questions about whether large language models spontaneously reproduce human errors. And people have indeed looked at this kind of from a psychology perspective. Probably for this audience, I don't need to remind you of Linda the bank teller or what the conjunction fallacy error is, right? Where humans tend to say, given a certain description, that it's more likely that Linda is a bank teller and active in the feminist movement than just a bank teller, even though this violates the laws of probability theory. Now, it wouldn't be interesting to show that a large language model gives you the preferred human answer on the Linda the bank teller case, because that's almost surely in the training set. So they try to give a slight variation. They think it's a novel version of this error. This is about being an artist, so they give you a artist who likes to read, and the prompt kind of cues up that she really likes to read. And again, unsurprisingly, The Chat GPT test gives you the so-called conjunction fallacy answer very often, maybe even a lot more often than the humans do. So it at least shows that it's recapitulating one of the errors. But again, this could be done by kind of approximate matching. The regurgitation in the training set doesn't have to be exact. We already know that these things do kind of stochastic matching to patterns in their training set, so I'm still not sure that this is actually definitive. And then there's an additional problem that these models make a lot of mistakes that humans don't make, right? So like adversarial perturbation or adversarial examples, you probably heard quite a lot about that. Um, Most generally in this area, I think it's very difficult philosophically to say which mistakes are acceptable and which mistakes ought to be disqualifying. And the difficulty is finding a kind of principled way to say that even when humans make really surprising mistakes, they're not disqualified from being reasoners, but then the stranger or not human typical mistakes that the machines make are disqualifying. It's very difficult to come up with a consistent set of principles to give those verdicts. If you want to get further into the attempt to do so, there's a nice paper by Alex Taylor, Bastos, Brown, and Allen that talks about a so-called signature testing approach where you have a kind of more theoretically driven approach to why certain errors are disqualifying and certain errors aren't based on, for example, an algorithmic conception of what the relevant inferential ability is. There's also some examples. So there were claims ambitiously made that these large language models have a theory of mind and they show human-like patterns of reasoning on theory of mind-like tasks. Tomer Ullman has an interesting paper where he used some of the same probes in standard kind of false belief type tasks and showed that these models don't give a response that humans would regard as kind of obvious. So you can give them a probe like, here's a bag filled with popcorn. There's no chocolate in the bag. The bag is of transparent plastic and you can see what's inside. Yet the label on the bag says chocolate, not popcorn. So the LLM still thinks there's the observer is going to say there's chocolate in the bag and just kind of ignoring the transparency. And so Ullman shows that it makes these errors across a variety of other conditions that, thought no human who understands how seeing works and comprehended the probe would make these types of mistakes. However, humans also make mistakes that you wouldn't think humans would make unless you actually look. So I just have to temper this a little bit. One of my favorite examples to talk about here is from Landy and Goldstone, where they show that humans make kind of howling mistakes even on simple arithmetic problems. So they vary the white space in very simple equations of this form, right? Where you say, for example, space out the addition operations or space out the multiplication operations. And if you group the addition operations, you group the multiplication, you group the addition operations and you space out the multiplication operations, then people are much more likely to make a order of operations mistake and get the wrong answer on the question. Whereas white space is supposed to be like formally irrelevant to the right answer. And you might say, does this show that humans don't know math? Or does it show that they're just like the machines, maybe using heuristics that work pretty well in their previous experience, but you can show systematically fail in out of distribution samples? Gary Lupion also has a number of papers in this regard and has been thinking about AI performance. He has this interesting paper with some howling mistakes. So, for example, people are less likely to report that scaling triangles are triangles, or they will sometimes say 798 is an odd number. And maybe you want to say these people are disqualified from being reasoners. I don't know, but people also sometimes make some really strange mistakes. Anyway, let's focus on the big query here before I run out of time. So the really interesting claims most recently have to do with O1, for the GPT-4 O1. And what O1 does is it's trained to self-prompt itself. Okay, so it uses these chain of thought prompts on itself, and it's trained through reinforcement learning to learn to do that adaptively. And OpenAI makes some pretty ambitious claims about the value of these self-prompting chains. It's meant to simulate sort of roles attributed to inner speech and human cognition. When you're kind of talking to yourself through a problem, taking your time and trying to attend to different aspects of evidence. Let me switch really quick. I think I have the window open. Yeah, okay. So you should see the OpenAI They have a number of demos, which I encourage everybody to do to take a look at. So with a grain of salt, these are industry demos and you don't really know what they did behind the scenes to get these results. But they have a number of reasoning test cases where they show O1's performance. And so one of them is a novel cipher. So they give a kind of difficult novel cipher to the problem, to the system. And then it's got this private self-prompting. So if you expand it in the demo, you can see all of the text it's producing for itself to try and solve the problem. And you can see it's kind of trying out intermediate hypotheses for what the cipher is, and then seeing what you'd get as a result of trying that approach to the cipher, and then seeing does that give you a kind of consistent message? If not, what do you need to go back and revise for the cipher, and so on. And these can go on for quite, it can produce 2,000, 3,000 words of self-prompting text before it actually gives an answer to the question. So quite sophisticated stuff appears to be going on there in the self-prompting. This is based on the idea that so-called chain of thought prompting can give you better results than without putting in intermediate steps of reasoning. So we learned pretty early on with transformers that if you give them a kind of math problem and you just ask for the answer flat out, it will very often get the answer wrong. But then if you give in your prompt a kind of example of intermediate reasoning, it will do a lot better. And we even learned that there are certain, this is, why prompt engineering became such a hot idea for a profession for students to aim at a few years ago. We learned there are simple little things you can prepend your prompt with, like let's think step by step or even just first, that could raise the accuracy of early models from only 17% to 78% on simple arithmetic and reasoning problems. Just to show you the power of this kind of approach, I was trying to get a failure mode from GPT-4o, and one of the things that they commonly failed on was counting letters in words. Unfortunately, GPT-4 got the right answer on my first couple attempts, but I finally got it to miscount in one of the common nicknames for Gainesville, Florida, my new home, which is Tree City, USA. And you can ask it now, okay, enumerate each letter independently in the prompt. And then it'll say, okay, sure, I'll try that. And it's really good at doing lists, right? And so if it actually lists out each letter independently, it almost always gets the right answer in that case. And so you can see here how the kind of scaffolding provided by internal self-prompting could help it do things like counting, which are relevant to math and so on. And now you can just imagine doing that for as long as it takes to kind of scaffold your way to the right answer on a difficult multi-step reasoning problem. This is, if you want to get more into the details of how the reinforcement learning for self-prompting works, you can look, for example, at this reflection paper, which goes into some of the detail with the X, right? But it's, again, inspired by thoughts about how humans reflect perhaps on inner speech. This is where they say some kind of really surprising and ambitious things about what they've then done with this model. So they say, we believe the hidden chain of thought presents a unique opportunity for monitoring models. Assuming it's faithful and legible, the hidden chain of thought allows us to read the mind of the model and understand its thought processes. This is where, as a philosopher, I want to say, really? Are you sure about that? As impressed as I am by these models, I think this is obviously kind of a gross overinterpretation of what these things are doing or what's going on. One thing that I think would be good to look at is philosophers and psychologists have thought a lot about inner speech and its role in reasoning for some time, and it remains controversial even amongst these experts, whether we think in inner speech, like whether that's kind of seeing our reasoning process itself, or whether we think with inner speech. And it just kind of gives you indirect evidence about what's going on, but definitely isn't giving you the actual mechanisms of reasoning itself. The idea is that while inner speech could be a private, grammatically structured representational medium, it might be incoherent to suppose that it's both globally broadcast to all kinds of different systems to coordinate reasoning activities and self-interpreting, right? And I think the real problem here is the OpenAI narrative here assumes that the speech is kind of self-interpreting to all systems that are consuming it in the same way that we understand what the speech is, that it's as meaningful to the system as it is to us as human readers and speakers of English. If you want a little bit more background in this, well before the advent of transformers, there's a nice paper by self-proclaimed radical connectionists O'Brien and Opie, where they make this point about inner speech that you might think, being aware of inner speech while you're reasoning tells you that you think in this language-like medium, but really it doesn't. The better way to look at it is it's just a kind of self-scaffolding. In the same way that like when a kid is learning to tie their shoes, they might recite a nursery rhyme about bunny ears and going under the log and so on, right? That helps them remember the steps of tying their shoes. That's just kind of a mnemonic device, right? A scaffolding to direct their attention in certain ways. It's not actually giving you the computational mechanism that they're using to reason about tying their shoes. Edouard Moschery has a nice paper too. He's actually from the other side. He just points out that the fact that some property P is represented by a thought doesn't license per se the inference that the thought itself possesses that property P. So what he means here is like, imagine a green triangle. That means you're representing a green triangle, sure, but it doesn't mean there's anything green or triangular in your head, and you still have no idea how it is that you're actually representing the green triangle. Similarly, the thought about these models is we see there's text produced. So sure, in some sense, they're representing whatever these words represent, but that doesn't mean we know anything about how they're interpreting those words or producing those words or consuming them, right? So what really matters, I think, for the questions we're interested in is whether they are producing or processing these tokens in a language-like way. And merely seeing the internal chains of thought doesn't tell us that. So what we're going to need to do is, I think, interpretability work to look inside the internal activations of the model and see what they're really doing. I'll finish one more thing. So I'll do a couple more minutes because this stuff is really fascinating, and I expect everybody will find this to be maybe the most interesting question, and then I'll stop. I think there's been some really interesting work recently trying to figure out what are the steps in these chain of thoughts actually doing, right? We have this kind of obvious prima facie interpretation, the one that OpenAI goes with, that you're actually seeing steps processing intermediary evidence that's relevant to actually solving the problem, right? But it's an open question whether that's right on the basis of new empirical results, right? So I've pushed back against this naive interpretation already, but there's even some more stringent ways to do so. In particular, there's a slightly less hopeful narrative that they're just chaining together islands of probability calculation that would be otherwise distant or inaccessible from one another. I'll show you what I mean by that in just a second with the graphic. And there's an even more skeptical interpretation of what's going on, that the text that these models are outputting in the internal chain of thoughts is just irrelevant. They just allow the transformer more inference time computation before answering. So one thing that differs about transformers from earlier vector-based language models, a lot of those were recurrent, right? Which meant you could kind of go through endless loops until you settled into a stable answer to the question and then answer. Transformers aren't like that. They're kind of a pass-forward model by and large. But if you continue to produce intermediary tokens before you give an answer to the question, it's kind of an indirect way of allowing the transformer to do more and more pass-throughs, where it's continually building a richer and richer internal representation through self-attention, and just devoting a lot more computation to the solution to the problem before it gives an answer. So let's go to the middle range option, that it's helping it chain together islands of local probability calculation that it wouldn't otherwise be able to make as accurate estimates. There's a paper by Goodman that makes this claim that's very interesting. So they say the idea is, well, the problem with a reasoning problem is you want to generalize beyond explicit combinations of variables that you've seen in your training set before, right? And the problem is that when you're generalizing, you don't have the right kind of evidence on the basis of in between variables to make an estimate of what the value of each of those intermediate variables should be when you're doing the reasoning jump, okay? So what chain of thought prompting can allow the model to do is that by producing sentences that kind of link together these islands of local probability calculation that are overlapping, it can now give kind of conditionally appropriate estimates of the values of the probabilities of all the intermediate variables by chaining together those probability calculations instead of kind of just estimating them independently of one another. And that makes all of the estimates of the intermediate variables in that particular context more reliable. They have some formal results where they show that if you take the chain together probability estimates versus the point-wise probability estimates, you can close what they call this reasoning gap and get much more accurate estimates on a variety of different reasoning type problems or problems we might think require reasoning. I think this is a very interesting approach. However, there are even more skeptical results, as I mentioned. So one thing people have done is they said, well, instead of training it to do semantically meaningful looking intermediate text, what if we just train it to produce a whole bunch of ellipses before it answers? And you also get a big benefit on reasoning problems just by getting it to output a bunch of ellipses before it answers, right? So this should be a little bit troubling if you have an expansive interpretation of what the internal self-prompting is doing, right? The mere fact that just outputting a bunch of dots before it answers improves performance also suggests that at least partial part of the benefit that we're getting is just this additional ability to put in more computation at inference time. There's other results that are kind of converging on the same answers. One trains them to do invisible pause tokens and also gets a benefit. But again, I always like to counterweight with humans. We always tell our students, you've got to stop saying and yeah and like so much and pausing so much in your lectures. But there are studies, for example, this one by Birkbeck and Dideo, about when people produce these kind of filler tokens in their own speech. And they show there's a big drop off typically in information throughput in the speech before the production of filler tokens. And then after the production of filler tokens, the information flow jumps way back up again, producing more high quality information flow in the conversation. So even in humans, the thought might be, this could be a way of discovering that filler tokens actually do have some adaptive benefit even in our own speech. Okay, I think I'll end there in interest of having some time for questions. What I would have said in the remaining 15–20% of the talk is that really what we need to do now, if you bought what I've said so far, is interventionists work to try to probe the internal workings of these systems and move them around to try to confirm or disconfirm representation level hypotheses about how they're actually producing the intermediate chain of thought tokens and how they're processing them. If you want to see more of that, I have a paper with Raphael Mirolier that you can find preprint of online. That's a review of all of those interventionist interpretability techniques and why we think they're more promising for answering this type of question. There's another philosophical story here too at the end about how even if you don't think these things are reasoning, they could still be regarded as pretty good models of textual culture of reasoning. And you could do a kind of abstraction process to try to figure out what the patterns of reasoning are that humans actually engage in various subcultures, for example, in scientific documents. And that could still be a very valuable source of evidence, especially for kind of digital humanities type projects. So if you want to hear more about that, feel free to follow up with me independently. But I think in order to have some questions, I'll end there. Okay, so takeaways, it's going to be very difficult to assess large language models as models of human reasoning on the basis of performance tests alone. It's more interesting to see whether they spontaneously reproduce errors indicating signature limits that match human signature limits on reasoning tests, but it's very difficult to fairly assess which errors are signature and which ones are disqualifying. And I think interpretability techniques are going to be the most promising method to really sort out interpretation of things like O1. Okay, I'll end there. Thank you.